as we know, software pervades our everyday lives, but as we have also seen, critical bugs still occur quite frequently. And so my dream is a future where this is no longer the case, where essentially we have critical bugs to be an extreme rarity. And so we have a dedicated discipline for that in computer science, which is called formal methods, which are mathematically rigorous techniques to make software more secure and verify it. And so formal methods have been researched over many decades. So there are many techniques with many tools. And there's also been many Turing Awards awarded for advances in this field. However, despite all this, formal methods have not been widely adopted in industry. So people are not using formal methods in their daily coding. And one of the key reasons for this is that formal methods are not mature enough. And so this is a real hindrance for their adoption. And so to realize my dream of a future where critical software bugs are extremely rare, we not only need formal methods, but, and this is the subject of this talk, we need formal methods engineering, FME, which is a new discipline to make formal methods more reliable, performant, and usable. And let me give you an analogy here. Software engineering is the field in computer science that systematizes software, development, maintenance, and management of software. And so, and in analogy, formal methods engineering should be the new field of systematizing formal methods. And so this new field, formal methods engineering, are characterized by three key challenges. The first challenge is how to make formal methods more mature. Because at the moment, formal methods are not reliable, not stable, not performant, and not user-friendly enough. And our end goal here is highly mature formal methods that everybody can use. The second challenge that we have is how to best utilize formal methods. Because we have, as I touched upon earlier, we have many techniques, testing, static analysis, verification, you name it. And the end goal here is maximum software reliability at minimal costs through a combination of these tools. And the third challenge is how can we best enable formal methods? Because we have a specification crisis. Most software is actually written without specification in mind, and neither with formal specification. And so our end goal here is systematize and effective processes for engineering specifications. So now these are huge challenges which cannot be solved by one researcher alone. This needs a dedicated community, the formal methods engineering community. And my contribution to, or my first step to establishing formal methods engineering is, as pointed on in the introduction, my research on solidifying modern SMT solvers, which found quite a number of bugs, out of which many were fixed and also many were critical soundness issues in SMT solvers, which are one of the most powerful and important formal methods. As a second contribution of this research, we also devised powerful tools to validate and test SMT solvers. And the third is that this research has enabled follow-up research on testing other formal methods software and made formal methods a benchmark in testing and software engineering in general. So having motivated this general idea, my vision of formal methods engineering, I will now talk about this specific contribution of solidifying modern SMT solvers in detail. Before I dive into deep details, let me first tell you what is an SMT solver. An SMT solver is a tool that's given a first-order logic formula like this one, x greater than 0 and x smaller than 0, or something more complicated, determines the satisfiability of that formula. It returns set along with an assignment or solution, and it returns unset if there's no such solution. SMT is a shorthand for satisfiability modulo theories, and the theories include stuff that is used in programming languages, big vectors, arrays, strings, integers, and such data types. So now we know what are SMT solvers. So let me now tell you why specifically I focus on SMT solvers here. Because SMT solvers are the foundation for so many other formal methods, like program verification, theorem proving, solver-aided programming, and program synthesis. All by themselves guarantee the reliability, trust, and ultimately the safety of our software. Besides being research foundations, SMT solvers are also used in large-scale industrial applications. For example, if you know Amazon Cykova, which is used for ensuring cloud security, it runs on a third of all cloud services worldwide. Then we have Adacore Spark, which is a verification suite for verifying cyber physical systems, and Microsoft's Seguro, a big tool that uses SMT solvers for verifying Azure networks. Because SMT solvers are so important, bugs in them can be really critical. So, for example, if an SMT solver gives unset on a satisfiable formula, like in this case, this indicates a critical soundness issue. If SMT solvers have soundness issues, this unsoundness can propagate to client tools, and we can no longer trust the software that builds on them. Likewise, if SMT solvers are slow or non-terminating, this can also propagate and disable the software that builds on SMT solvers. So my research goal here is solidifying modern SMT solvers, making sure that they are correct and performant. And this research is guided by 3 consecutive research questions. So first of all, do SMT solvers even have critical bugs? How do we effectively test SMT solvers? And have we tested the SMT solvers enough? And I will structure and talk along these 3 research questions. So do SMT solvers even have critical bugs? To approach this first question, we have to start from the very beginning, which is in June 2019. If you looked at GitHub issue trackers of the 2 most popular SMT solvers, Z3 and CVC4, you wouldn't find much at the time because there were not many critical bugs reported. The same goes for solver competitions, which are yearly held. It was known that there are some issues, but not at large. And the research at the time just found 6 bugs in mostly unstable solvers and theories, all of which indicated that we can trust the SMT solvers on the whole. So this guy said that assumptions are made and most assumptions are wrong. In this spirit, we can approach the problem and put SMT solvers to the test. And the key question here is, how can we do it? There are 2 key challenges here. The first one is to fabricate complex test formulas to thoroughly test the solver logic. And this is challenging because the solvers themselves they have a lot of logic. They have over 250,000 to 500,000 lines of code with a complex input format supporting all combinations of features that are useful for programming. And the second challenge is, how can we validate the solver's result? How can we solve the oracle problem? And this is difficult because when we want to generate complex tests to stress test SMT solvers, we also want to know what the ground truth of those tests are. And this is a trade-off. I will now introduce you a technique called semantic fusion, which solves both these challenges. So before I start, I just give you a quick idea on how SMT solvers used to be tested. So this here is a set of benchmarks with a lot of formulas, 300K real-world queries that are used by applications, research papers, and whatnot. Since SMT solvers are tested on these formulas for years, they are not interesting because SMT solvers just know, or they just don't fail on these formulas. So in order to create two more interesting formulas, the iteration is to take the existing tests and multiply them. And we do that in a fancy way, such that we get not only the Cartesian product, but more. And so intuitively, what do we get here? We get complex real-world-like queries by a fancy way of combining these two test sets. And so let me concretize this. Given two formulas, phi1 and phi2, we first concatenate them, and then we slice off two pieces of these respective formulas, and then we combine them in an interesting manner. And we do this randomly, so we can do this in many, many ways, and as a result, we get many, many tests. And we do this with so-called fusion and inversion functions, which are new terms that we introduce, and then essentially we have the black and the white dot, and we introduce a new variable z with respect to these two dots, and then we retrieve the original or equivalent terms with respect to the white and the red, white and the black dot. So how does this work? So given two satisfiable formulas that you see here, phi1 and phi2, we first concatenate them, which yields a satisfiable formula. And now we do the crucial step. We use a variable z for combining the two subformulas, and then we equate this variable z to x plus y, and we call this the fusion function. And then using this fusion function, we deduce terms for x and y that we call the inversion functions. And now we can take these inversion functions and plug them back into the formula at random places. Occurrence of x and y could also be the first one, could be the second one for y. We can also do this step multiple times. And the crucial thing here is that we have proved this to yield a satisfiable formula no matter how we do it. And that's how we gain so many different satisfiable formulas useful for testing. So we did this idea for a set, unset, and mixed pairs of formulas, and then a bunch of fusion and inversion functions for strings, integers, and reals. And with that, we could test the SMT solvers. And we implemented all this in a tool that we call Yin-Yang. Did 4 months of extensive testing of the SMT solvers, Z3 and CVC4, the two most popular. And now we can ask the question again, do SMT solvers even have critical bugs? And the answer is quite surprising and also a bit shocking. Yes, they do. And in fact, they have quite a lot of bugs. So in total, we found 76 bugs that we reported to the developers in both solvers, although more in Z3 as compared to CVC4. Most of these bugs were actually confirmed, and most of them were soundness issues, so wrong results. And what's even more striking is that many of these bugs were actually undetected for years, and they were latent in the solvers. Since 3.5 years, were 8 bugs in Z3, 8 incorrect results. And the same also for CVC4 in 1.5 years. So what you may ask now is here, why is this concerning? Why should I care about this? And the answer is because these incorrect results could have propagated to your client tools without you even noticing. So just to give you some concrete idea on what kind of bugs we are talking about here, look at this formula, which has just two variables, both integers, implementing a simple integer division a divided by b equals -1. So clearly, this formula should be satisfiable, right? We could just assign a 1 and b -1, and that should do it, right? Or the other way around. But if we give this simple formula to CVC4, it would return unset, which is a critical issue. And we have much more bugs like this, which I cannot show for the sake of time. So do SMT solvers even have critical bugs? Yes, they do, and in fact, quite a few. And this had an eye-opening effect to the software community and yielded us a distinguished paper award at PLDI 2020. So with that, this idea of semantic fusion was a very targeted attack, which was most effective for nonlinear and string theories. The question now that we had is, can we do something more general that we can use on all kinds of formulas? In other words, how can we more effectively test SMT solvers? And I'll start by the question, what is central to the semantic of SMT? And the answer is operators. Why is that the case? Because operators critically affect the solution space of formulas. If you change operators, if you change a plus to a division operator or something else, that will radically change the meaning and solution space of the formula. So here's a very, very simple idea. Why not mutate operators according to their types and get lots and lots of new formulas for testing? And so you can do this like this. You take formula like this, and you can differentially test two SMT solvers, cross-check them against each other, and then randomly pick an operator, for example, the greater operator in this case. And the greater operator takes two integer expressions. And so we can mutate this greater operator by equals, not equals, smaller than, greater equals, and so on. And so let's assume we chose equals. And so what happens now is that this wasn't already enough to trigger a bug. And so again, what does this formula mean? This formula actually means for all a, there exists a b such that 2 times b equals a. In other words, this formula means every integer is even. And so, of course, this should be unset, and it's not the case, right? But Z3 returns set, which apparently thinks every integer is even. So also with this idea, we implemented testing campaign and on the same solvers and could apply this to more benchmarks. And what did we find? There were so many bugs. There were 1,200 something bugs, almost everywhere in all different theories and logics. Again, even greater shock. And so we had this super effective technique, but of course it was limited in a way that formulas would roughly stay at the same size. So we thought of something even more effective, and we extended this idea by being able to mutate expressions and found another around 237 bugs. I'll skip this for the sake of time. So how to effectively test SMT solvers? The answer is by mutating operators in expressions, which led to over 1,500 bugs in SMT solvers. So the final question is, have we tested SMT solvers enough? And first, let me tell you why existing SMT testers cannot tell you that. Because existing testing is unsystematic, producing large bug triggers without guarantees, missing bugs. For example, such a super small bug has been missed for quite a number of years, implementing a simple trigonometric equation of tangents and sinus, which is satisfiable, but the SMT solver returned unsettled on this one. So the crucial question here is, what can we learn from small bugs like this? And there's, in the literature, if we dig deeper, there's a small scope hypothesis by Daniel Jackson from MIT, who said basically most interesting behavior of software is observable on small inputs. And we found this on SMT solver bugs as well. And so the question was, can we exploit this? And we came up with something, and this is called grammar-based enumeration, which is the idea of enumerating the smallest inputs from a grammar, a context-free grammar, up to larger inputs. And this has several great benefits. It's systematic, it produces small bug triggers, it yields bounded guarantees, and as we will later see, it can be used to judge evolution of the software. So if we implemented this as a tool called ET, a grammar and a dedicated number of tests as its input. So I will skip the details here a bit. It's basically a compilation into a Haskell library that realizes a random access to the formula space, and then we again cross-check the SMT solvers. So have we tested enough? Well, what does enough mean? It does mean no bugs found by this new tool ET, which does bounded exhaustive enumeration. Under the assumption that all bugs have small triggers, and we also constrain to the given set of logics and constraints on the structure of the formulas. So what did we find? Again, of course, bugs, like 100-something bugs. And perhaps much more important than the bug itself, what we found is after a while of testing, we did not find any simple bugs anymore, which means that these solvers at least don't have such simple bugs as the division A divided by B or something similar. The bugs that remain are guaranteed to be more complicated. And with this idea, we also judged the reliability of the SMT solvers and found that SMT solvers' reliability has greatly improved over time. So have we tested enough? The answer is yes, correctness has improved significantly. That doesn't mean that there are no bugs in SMT solvers anymore, but they have become much better. So now, to conclude, I will want to shortly give some more ideas on this vision of formal methods engineering again, which is this dream. We have this dream of making software bugs extremely rare. And for that, I proposed formal methods engineering. And one first leap to that was my body on research body on solidifying SMT solvers. So in difference to software engineering, which is a holistic, user-centric, and pragmatic discipline, and formal methods, which is a reductionist and theoretical and a discipline that aims at universal results, formal methods engineering should be holistic, user-centric, theoretical, and pragmatic at the same time. And I also showed you some of the key challenges, how to make formal methods more mature, how to best utilize formal methods, and how to best enable formal methods. And I want to quickly dive into each one of them. So there are 4 aspects for making formal methods more mature: reliability, stability, performance, and user friendliness. I have addressed reliability for SMT solvers largely, but is open for many other formal methods. Stability is open for almost all the formal methods, including SMT solvers, and performance is largely addressed at a divide and conquer a low level, while not as a holistic system level. And user friendliness is largely unaddressed. And how can we best utilize formal methods? I proposed the software validation problem, which is we have a bunch of components of software that are interconnected. We have a set of formal methods, and what we want is a cost guarantee mapping from component and method to the costs and guarantees it yields. And we want to generalize this to as much as possible to all kinds of software. And besides devising a theory, this should actually be a practical system that can exploit this, a validation black box that maximizes guarantees and minimizes costs. And finally, for addressing how to best enable formal methods, we need something like empirical software engineering for formal methods. Because empirical software engineering has had a super great impact. It produced Scrum, CI/CD pipelines, waterfall model. We need the same thing for empirical formal. We need the same thing for formal methods as well. So in sum, I showed you 2 things: my vision, formal methods engineering, and then I showed you one specific contribution that I made as a first step towards this: solidifying modern SMT solvers. One of the most important and fundamental formal methods, along 3 research questions. Yeah, and with that, I'm at the end of my talk and look forward to the discussion.